Hello and welcome. My name is Ali Kashani. I'm assistant professor at the University of New South Wales in Sydney, Australia. Today I'm going to talk about construction automation via 3D printing. If you look at the car manufacturing industry more than 50 years ago, car was a luxury item that not everyone can afford. But since then, things has been changed, and you can see use of many robots, not doing all the process that it happens during the car making, but most of it. So we can see that the automation has been increased. That end up in reduction of the cost in terms of making the cars. So the customers can afford a car at much lower cost than it was compared to the income compared to the 50 years ago. But if we compare it to the construction industry, so more than 50 years ago, everything has been done by hand, and the thing is that construction labor cost at the time was a few dollars per day. But nowadays, we almost do the same thing. Maybe we improved safety a little bit, but still you cannot see much automation happening in day-to-day construction. But because of the other factors and construction labor cost has been increased massively. So if you look at in Australia, our basic labor cost is going to be $75 to $85 per hour, which ended up in increasing the building cost. So if you look at the building cost index from 1967 to 2018, you can see that it has been exponentially increasing both in residential infrastructure and non-residential building. There are many factors involved, but one factor is lack of automation, and very high labor costs resulted in higher construction cost. And as a result, these higher construction costs result in less affordable houses, and that is something that has been affected the younger generation, those who cannot afford to have their own house. So if you look at the construction costs around the world, Sydney has one of the most expensive construction costs, where I live. There are other cities, as you know, London, New York, San Francisco, Los Angeles. So you can see that the cost of commercial property, multi-unit high-rise and hotels, etc., you can see that how expensive it is based on this figure. And this is also happening not only in those cities around the world, but at different paces. So what we can do, one thing that can be done if we compare to the example of the car manufacturing industry, which productivity has increased, but the cost has been decreased since inclusion of the automation in the car manufacturing industry. The same thing can happen, and it's already happening. It's not something that we haven't done it before. We gradually increasing automation, so sort of like building information modeling and Internet of Things, etc. But there is also other concept that can be used that they call it future-proof design and construction. So those like of the thing that we call it as a digital construction, and 3D printing is one of those. I had a chance to get a fellowship to travel to few different countries around the world that they actually doing some greatest stuff in terms of digital construction and concrete 3D printing, which I highlighted those in my reports. My Churchill Fellowship report, which is available. So some of those companies I already and institutions I already put the names there, and I'm going to discuss some of those projects in my presentation today. There are many other projects that has happened since then. So this report is for almost 2 years ago, and it's very good to see that the scale of the project that is happening at the moment. So one of the things that I really inspired by is that nest building at EMPA in Switzerland. So which they really help in terms of innovation and prototyping of those future concept of innovation, which as you can see is the empty cantilever building, which in each part new project that is based on the outcome of the researchers, the thing that they want to prototype, the Swiss researchers, they can use and show it. And one of those project that is really interesting is the DFAB house, or digitally fabricated house, which has been done in collaboration by ETH researchers. So if you look at the DFAB house website and the nest building, you can find more about what is included. So anything that use of the robots or digitally fabricated and assembled timber structures, 3D printing things, and everything is available in the fabrication of that house, which is pretty amazing. But let's focus on one aspect of that, which is 3D printing. And there are many other projects that's happening around the world. And one of them, which is really interesting and passed through rigorous standard in Germany, is the 3D printing of a house by Perry Group using cobot printer technology, which you can see in this video. As you can see, all elements of the building during the construction can be installed while the concrete is in fresh properties, which is saving time in terms of later adding those pipes and other things that you need to include in a building construction. So if you look at the end result, it's going to be something fantastic like this, which also provide that unique element of architectural design as well. So this is another example. This is the biggest on-site construction 3D printing that has happened in United Arab Emirates. And if you see, you can compare with the photo that I showed earlier. The number of people that is on site, only a handful, less than a handful of people are on site just for supervision and doing not much. As you can see, they're just laying down or sitting to see that if everything is going all right. So that would be the future of construction, the thing that you'll see that's gonna happen in the future. So, and that is the end result. Okay, so I just want to give, probably some of you has already seen those projects or heard from those projects, but I just want to cover a little bit of background. What do I mean by construction 3D printing? The other thing that I want to touch base on is sustainability. So nowadays we talk a lot about the climate change or emission and how we can reduce it and how we can be more sustainable in construction, etc. The thing is that construction 3D printing also can provide you that sustainability that we need for construction. So we know that the sustainability is on 3 pillars of social, environmental, and economic. In order to say like one technology is sustainable, we need to look at all these 3 pillars. So let me go through these pillars step by step and say that why construction 3D printing can help with all these 3 elements. So first thing, and perhaps the most important thing, is the economic factor. Because if the economic factor doesn't doesn't sound, or is something that is going to at much higher premium, that wouldn't be sustainable. That wouldn't be something that industry can take on. So why we think that 3D printing is more economic? So first of all, you're going to eliminate the form work. And also it comes with a reduction of the labor cost. So if you look at the concrete structures, and very easy form work, rectangular one, even for that, including labor and material, is going to be almost 50% of the cost is that. So, and 3D printing doesn't require any form work. So that's almost 50% of the cost element, it can be removed. The other thing is about the faster production and reducing the project lead time. Most of the construction project is going overdue, and that is going to be something that it's not desired, and it's going to increase the cost of the projects to the customers and also to the builders. But as you can see, because 3D printing can be something that you can run it 24 hours. You can see that in the project in Dubai, they use it, in UAE, they use it overnight. So that's, you can accelerate the construction process. So that's our two main reasons, and also there are many other reasons might be involved in terms of providing the economic factor. The other pillars of sustainability is about the social impact. So what can 3D printing and use of the robots and automation can provide us in terms of the social impact? So first of all, extra safety, reliability, accuracy, and reduce the needs for skilled workers in remote places or dangerous sites. So around the world, we have areas that with very harsh climates, and we put the construction workers in those climate for construction. It's not safe, and it reduces the accuracy, and it increases the risk. So using the robots in those areas can help in order to reduce the risk by using the robots. And also in some remote places, so there is lack of skilled workers. So using the robots that can provide that advantage in terms of construction. The other aspect of that is the end results. We know that natural disasters can happen around the world. So we've got flood, bushfires, earthquakes. And after that, governments are in desperate needs for some accommodation. So, and in some places you might have some places that you can move people into, but in some other places using tents might not be safe or wouldn't be available. So you need some kind of more sturdy accommodation. And that is something during the nature of concrete 3D printing, it doesn't need to be that sophisticated, but it can provide some shelter within a day or two. That's something that can happen. And also, if you look at it, can provide affordable houses for homeless people. So, like of the project that has been done by New Story and Icon in United States, that they can print houses in an affordable way and then give it to people with low income class or people around the world with poor people that cannot afford houses. So that's another social impact of concrete 3D printing. But we can also look at the environmental impact. So what are those environmental impacts that concrete 3D printing can provide? So we know that based on free-form design, we can use less material in order to develop the structures that we need. And it doesn't need to be basic rectangular cylinder shapes that we used to use in our construction. So it can be other shapes that still provide that structural integrity without using much material. and with less weight, less waste, and less transportation, so which also indirectly is going to affect the climate change in terms of the CO2 production, etc. So those are elements in terms of less waste, using less materials, and this kind of thing. It can help with the environmental factor. Because we know that cement is one of the most pollutant material, and is base things in order to, in the concrete 3D printing mixes. But on the other hand, we can use less material that can offset that in terms of overall use of the cement in the structures. So it's one example of that. For example, this is truss. Instead of like have a filled cylinder column, we can have a structure like this that can provide the same performance but using less material, and also it's more aesthetically pleasing as well. The other advantage of construction 3D printing is in mass construction. We know that we need mass construction because our population is growing and we need more houses and we need affordable houses. But if you want to have different designs, if you want to, for example, a new neighborhood that you want to build new houses, if you want each of those have different designs, then it would be less to increase the cost of the construction, and it would be less affordable for people. So it's very common that they use this kind of mass construction. So most houses in a new neighborhood are more or less look the same, which is not appealing, and it doesn't also provide the value for the owner of this house, because there are many houses with the same features and same design, etc. And but the problem is that if you want to change the design, the cost of the construction is going to increase, etc. But 3D printing houses, because you can have a freedom of design to some extent, then you can just use computational design in order to design your house in different methods. And as soon as it's ticks some of the boxes in terms of being a sturdy enough in terms of the structure and during the printing, then you can the sky is the limit in terms of different designs that you can use. So in that way, you can have houses that's going to be affordable, but also different design and unique designs, and each house has its own character. So that part of it, of 3D printing, can provide with affordable and artistic construction that we can hopefully see in the future. And one of the example of that is the village in Netherlands, which you can see artist views on the bottom of this page. One of those houses has been already printed and has been inhabited, but the others are also in the progress in terms of the construction. And 3D printing does not only give you houses, you can also build bridges. And it doesn't need to be concrete. You can also use metal. In this project you can see. And the great example of that is the first 3D printed steel bridge in Amsterdam by MX3D, which is fabulous. And also other project, for example, this telecom tower by X3 that has been 3D printed and prefabricated into different elements and then assembled on site in order to give that telecom tower. It can also be the landscape furniture. So for example, again by X3E, that's landscaping furniture that you can see in this video. Or it can be just a facade, like this project also in Netherlands, that they use instead of like asking the residents of the building to evacuate in terms of renovation of the facade of the building and take it out and replace it, they use the own facade, and then they just add an element of the 3D printed on top of that you can see in this video, which can save a lot of cost in terms of accommodation for those people that needs to be removed, and also it provides a much better aesthetic view to the building. So this project at the moment is under progress, and hopefully it will be sometime soon. Okay, so these are some of the things that I wanted to show to different types of the project that has been happening, and there are heaps more projects that are happening at the moment around the world. But being a concrete person, I just want to mention that what are the key challenges in concrete design and technology that has been developed more than few decades, and what do we need, and what are the differences for 3D printing concrete. So let's look at this. First of all, we have been developing concrete as something that you can easily compact it with high fluidity, but not too much fluidity that can affect the strength and can provide bleeding, etc. But on the opposite side, for 3D printing concrete, there are two things that we mainly need during the process of the 3D printing. Although that's all those strength requirement and everything needs to pass, but during the printing, we need something that's doesn't deform after the extrusion. So one of the method of the concrete 3D printing is just extrusion. So we just extrude the concrete, and we got the printed filaments, and then on top of that we build up the filaments. So the filament that we print, compared to the traditional concrete that needs to flow and gets compacted, that one, it should have like zero slump, so it shouldn't flow. So that we call it shape stability. So it needs to retain its shape. And on top of that, at 3D printing, we don't have formwork. So there would be some lateral pressure and also vertical pressure on the bottom layers. That's, there is no formwork to hold that. So the layers must hold that pressure that comes from the successive layer. So that's another thing. So it needs to get this earlier strength as quickly, within like minutes rather than hours. The other thing is about the rebar reinforcements. So we had the traditional rebar reinforcement that we put into the formwork, and then we pour the concrete, and because the concrete is fluid, it just feels between the reinforcement, and everything is good. But the method of 3D printing, because we put everything layer by layer, inclusion of the traditional rebar reinforcement is going to be challenging. So that's something that's there are some method has been introduced, but there is a lot of more things needs to be done in order we can achieve something similar compared to the traditional concrete. The other thing is about the drying, shrinkage, cracking. So that's also again comes with the removing of the formwork, because that formwork helps the material stay moist during the first 48 hours, and help to reduce escaping of the water and drying, shrinkage, cracking. So that is not the thing that we have in concrete 3D printing, although that's in some enclosed environments, or even some companies using like moisting using like mists and spraying water, etc., in order to make sure that the concrete surface is moist. But still is something problematic, and that also comes that the concrete itself, most of it doesn't have coarse aggregates, and also the aggregates to bind a ratio, it's much less compared to the traditional concrete, which also increase the chance of drawing shrinkage. But in overall, durability performance of 3D printing concrete is not well known at this stage, and only limited research has been done in terms of the durability and performance. So as you can see, there's a lot of things that needs to be understood before we can say that the 3D printing is going to be the method of the construction within the next 5 or 10 years. So still progressing, but I can surely say that the progress has been very, very fast. And although I thought that maybe it takes 10 to 20 years until we get there as a eligible method of construction, but nowadays I think that probably that can be reduced even up to 5 years, because the progress has been very fast. Okay, so what do we do? So this is our lab, digital construction lab at UNSW. As you can see, we use 2 robots that we want to mimic the collaborative way that's happened in the construction. So construction is not something that one person do. So we want to mimic that. What are the things that 2 robots, and hopefully in the future more robots, can do together in order to build something. And that is our aim at Digital Construction Lab at UNSW. So our focus area is mainly going around the material development, and on top of that we have structural engineering, design and modeling, and we also look at the process optimization, robotics, and also using artificial intelligence, which is some of those projects are more advanced, and some of those projects that we just started. So these are lists of the projects that we are currently doing. Our PhD students and master students at University of New South Wales, which come with the mixture optimization, fiber reinforcement, lightweight concrete. We got the topology optimization using AI and machine learning to develop mixture designs, and sustainable low cement mixtures, and optimizing nozzle design, etc. But today I'm going to mostly cover some of the work that 2 of our senior PhD students has been done during the last couple of years, Mohsen and Hamid. So the first thing that I want to cover is that effect of the rheology in concrete 3D printing. So what I would say that is a triangle of concrete 3D printing, for specifically for extrusion-based concrete. There are other methods of the construction 3D printing as well. And in that case, we have 3 elements which we discussed, like the shape stability, like avoiding the formation of the layers of the printing, and buildability, like how many layers we can put on top of each other before it collapses. And the other thing is about the pumpability. So because we need to pump the material into the nozzle and then extrude it, so if the material is too stiff for pumping purposes, that it would be another hurdle that our material wouldn't fit for construction 3D printing. For this reason, we measured yield stress of the material. So, and based on that, we can say that if we achieve those 3 elements, so the first element was the shape stability. So material needs to have enough yield stress at the start in order to keep its shape and it doesn't flow. So, and that can be different based on the different parameters and the size of the filaments, but can be something from 250 Pascal to way above 1000 Pascal. And the other thing is this pumpability. So, there is a threshold based on the performance of the pump and the nozzle size, etc. That's and also the distance that you pump it. And above the certain yield stress, you cannot pump and extrude the material, which is another line, is the extrudability limit. And the time that you have from the start until you reach that point, you cannot extrude the material anymore. It's just your open time. So that's the time that you have for a batch to be printed. But that time starts with adding water. So if the process is just continuous mixture of and adding water as the printing progress continues, then you shouldn't have any issue with open time. But the most important thing is the buildability limit. So as I mentioned, so when you print the materials, you go layer by layer, and after a while, you build up the pressure on the bottom layers, and they might collapse. So you need to have the printed layers to get the strength after time, which we say like certain slope of getting stress versus time needs to be there in order to material doesn't collapse, and we call it the buildability limit, as you can see here. So these are the two theoretical mortar yield stress evolution. As see, one of them is good in terms of the shape stability. So initial yield stress is quite high, and then it's you just start your printing. But the problem is that it gets set very quickly, and then you got the pumpability issue. So that can be one thing. The other material that you might have, which the initial yield stress is good, but the material doesn't develop a strength quick enough. As you can see, at some stage, it's going to cross the buildability limit, and that's the part that's your 3D printed filament is going to collapse or squish. On the other hand, if you look at two other theoretical mortar yield stress evolution, you can see these two, which passing the both three requirements of pumpability, shape stability, and the buildability, although that they have different characteristics. And based on that figure of the static yield stress versus time, you can see that how your material is going to perform versus those three we say printing window, like shape stability line, buildability line. And you can see, for example, by that by increasing the water, that buildability limit might decrease, or if you adding more superplasticizer, the same also happens. So compared to the traditional concrete, adding more superplasticizer can help with better fluidity, but in 3D printing, having too much superplasticizer doesn't help with the buildability of the material. So that's one way that we can look at the rheology and the buildability measurements for concrete 3D printing, which we use rheometer. There are also two other methods that we use, which is one is the green compressive strength, and the other is one is the ram extruder, which I would explain what we do and what we get from those methods. So first, when we look at the rheometer, we can just measure the static or dynamic yield stress. As you can see in this graph versus time, and see that how the strength of the material is developed. Is it higher than the slope of the buildability, or is it lower? What is the initial yield stress? Is it higher than the shape stability? Is it lower? Which those limits, it depends on the size of the nozzle, the printing speed, the length that you are printing, and volumetric flow rate and other factors that can affect those limits, which I'm not going to go through it in details. But that's the parameter that affecting the buildability limit, and you can just check your stress development versus those buildability limit and see that if the material is passing or not. The other method is just a ram extruder, as you can see, like a piston that goes inside the barrel, and we put the material in, compacted, and just apply pressure at different rates. And what we can get, we can just see that sudden increase in the force, which is based on the compaction of the material, and then it's getting steady, which that force can be translated into the yield stress of the material, and that also we can get better understanding about the pumpability of material at different time. And also we can check different nozzles and the performance of the different nozzle using the ram extruder method. The other method that we use is the grain compressive strength. So we have filaments that can be different shapes. We have different shapes. It can be a disc, or it can be a rectangular filament, which is prepared in a special mold, and then you can apply pressure and see that's how the grain strength of the material is developing versus time. And that mimics the way that the layers are going to build on top of the bottom layers in 3D printing, and the pressure that is exerted by successive layers versus time. And we can use it in a continuous way, or we can use it in a step-by-step based on the interlayer time between each layer. And after, depends on the setting of time of the material, we can run this test until we reach those setting time, and after that the material is going to be stiff enough to get the strength requirement. So based on those methods that we discussed, we can see that if the material that we're developing is going to be printable or not, and then based on that, we are using it in different projects. So this project is talking about like a facade, wall, and insulator elements that we can use in the building, which can use a parametric design in terms of providing in a single layer, double layer, and providing all the G-code and parametric design using the grasshopper, as you can see in the slide. The other thing that's we are working, and also part of the collaboration within robots, is just using the micro reinforcement between layers, because that's the area that is very weak in terms of might be in terms of the bonding, and also providing the tensile strength that we can use the vertical reinforcements and horizontal reinforcement between layers. The other thing that's we have been doing, and the early result of that has been published, is about the shrinkage cracking concrete 3D printing, which we discuss about, like limitation using of coarse aggregate, higher amount of cement, lower water to cement ratio, and accelerated setting time. All those parameters can affect the shrinkage cracking, as you can see in the picture in this slide. So in terms of the shrinkage cracking, there are different parameters that can affect that on top of the material itself, like especially like in outside 3D printing. It's going to be temperature and relative humidity if there is any wind, and also the nature of the 3D printing, because we got a free form, and we got the much higher surface to volume ratio that provide an environment for excess moisture loss. And also we got a layered structure, and between the layers, so we got interlayer gaps or cold joints that might happen between the layers. So all those parameters are important. But in our study, we looked at the effect of the relative humidity, temperature, surface to volume, and sand to cement content, and see that how these parameters can affect the shrinkage behavior of the material. So we use two standards, and the reason we use these two standards because the sample size are different. So based on that, you can also look at the surface to volume ratio and effect of that in 3D printing. So we just use the control as per standard, and also the free form, which we, instead of like having the samples inside the mold for 24 hours, we took it out after the initial setting time has happened at almost 4 hours, and then put the sample in different constant temperature and humidity environment, which are either 24 degree, 50% humidity, 35 degree Celsius, 85% humidity, or 35 degree Celsius, 45% humidity. And we use different sand to cement ratios of between 0.8 and 1. So this slide shows the effect of those free-form condition and different temperature and humidity and the compressive strength. So if you can see that those free-form condition actually doesn't allow the material to get hydrated, which is very important during that first 24 hours. And you can see the differences here. And especially when we got the lower relative humidity and lower temperature, you can see that the difference in terms of the strength is massive compared to the environment that you allow the material to get cured inside the mold for 24 hours. So there is not much moisture loss. But if the environment provides high percentage humidity, as you can see in the case of the 85% humidity at higher temperature, or even like higher temperature itself, because it can accelerate the reaction at this at the earliest stages before too much moisture loss has happened. So that also can compensate some of the lack of hydration by removing the formwork. And if you look at the drying shrinkage, we find that some things I would say strange, also is very interesting. That's you can see that control sample at the start, they show within the first 28 days much higher shrinkage compared to the free-form sample. So these are black dots. And but after a while, you can see the samples that has been made in the environment with lower percentage humidity. You can see that the drying shrinkage is keep building up until 168 days. But for the samples that we had, that we keep it as a free form, so we took out the samples after 4.5 hours and put it in the 85% humidity. You can see that those excess humidity that we have can't just mask the effect of drying shrinkage, so not much drying shrinkage happening over the time. And also you can look at the effect of the sand to cement ratio. So that's hollow shapes showing that the samples with much higher sand contents compared to the field shapes. You can see that having higher percentage of the sand in the sample can help with decreasing of the drying shrinkage. But if you also look at the mass loss versus drying shrinkage, so for the controlled sample environment, we know that the mass loss is going to increase while the drying shrinkage is going to increase. But for the free-form sample, we realized that that the opposite is happening. So the mass loss at the start is very high, and that is because of the moisture loss during the first 24 hours. That is excessive, and then after that the mass loss is going to decrease while the drying shrinkage is going to increase. And that's part of that is just because we have a lot of unhydrated material inside the sample, so some of those can happen like based on getting the moisture from the environment and hydration. And also we've seen that the carbonation is also happening, and that carbonation also provide extra water for hydration to happen in. So some element of the carbonation shrinkage is also there. So this result we need to study more, but provide some interesting outputs in terms of what's happening when we're looking at free-form shrinkage. Okay, just to wrap up, I wanted to show this video and picture of something that we printed in our lab. So it's the letter U, which is the first letter of the UNSW. And by that, I just want to thank you all for listening to me today, and I'm happy to take questions. Thank you.